Hello everyone, welcome to my channel. And in today's video we are gonna discuss two problems of quantum mechanics that were asked in CSIR NET July 2025 exam, that is in the recent exam. So let us start. This is the question number 1, and it is given that a particle of mass m is in the third energizing state of an infinite potential well of width a. The time interval in which the phase of this wave function changes by 2 pi is. So we have these 4 options and we have to solve this question and choose which option is correct. Okay, so what we are given a particle of mass m which is in an infinite potential well of width a in the third energizing state. Okay, that means n is equal to 3 here. So and we have to find the time interval, so that means the expression of time in which the phase of this wave function changes by 2 pi. Okay, so let us come to the solution now. We know that for a particle in an infinite potential well of width a, the wave function for third energizing state at time t equal to 0 is given by this. Okay, so in general you may know that the expression is given by psi n and here psi n x0 is equal to under root 2 by a sine n pi x by a. But since here we have the third energizing state, so n is equal to 3 here, so we have taken psi 3 and this here it becomes 3 pi x by a. Okay, so we have this wave function for the third energizing state. So now at any time t, the wave function is given by this. So this was at time t equal to 0. So if we write the wave function at any time t, we will get this expression, that is this extra time factor will come along with this wave function. This is the same wave function as this one, so this was the space part, and now we have added the time part here. We have this exponential part is the time part, and this is the phase. The phase it was asked in the question. This phase, this is the phase. The phase of the wave function is this power of the exponential is the phase. Okay, and this E3, we have this exponential power minus iota E3t by h cut. So where E3 is this expression, E3 is the 9 pi square h square divided by 2m a square. So it is the energy of the third level. E3 is the energy of the third level. In general, we have En is equal to n square pi square h square upon 2m a square. But since here n is equal to 3, so 3 the square of 3 becomes 9. So 9 pi square h square divided by 2m a square is the energy of the third level. Okay. So now we have given that in the time interval t, the phase changes by 2 pi. So we can write this, we can equate this psi x0 exponential iota minus iota e3t by h cut is equal to this. Here what we have done, we have equated this wave function, into this where the phase changes by 2 pi, because it is said in the question that the phase changes by 2 pi. So here in the place of this phase, we have taken this minus iota 2 pi. Okay, so 2 pi is the phase. So now this is same, so this gets cancelled out. So now let us simplify in the next step. Now we have this exponential minus iota e3t by h cut is equal to exponential minus iota 2 pi. So we could have taken this as plus iota 2 pi, but since here a minus is there, so we have taken this minus, so that this minus gets cancelled out. So in the next step we just took logarithm on both sides, and this exponential got cancelled out, and we are left with e3t by h cut is equal to 2 pi, and then we found t equal to 2 pi h cut divided by e3, and then we substituted the value of e3 from here, that is 9 pi square h cut square divided by 2 ma square, and after simplification we got t is equal to 4ma square divided by 9 pi h cut. Okay, so it is given in the option 2. So option 2 is correct, as you can also see here. In option 2 you got 4 pi m square 4ma square divided by 9 pi h cut, which is the exact expression of t we get. Okay, so I hope this question is clear. Now let's go to the next question. In the question number 2, we are given that the energy eigenstates of a one-dimensional harmonic oscillator are denoted by the ket vector I, where I is equal to 0, 1, 2, 3 and so on. So if the momentum operator P cap satisfies this expression, then we have to find the value of n. Okay, so we are given a one-dimensional harmonic oscillator and the ket vector I is equal to 0, 1, 2, 3 etc., and we are given a expression and we have to find the value of n. Okay, let us come to the solution. So here, coming to the solution, for a 1D harmonic oscillator, the momentum operator is given by this. Okay, the momentum operator is given by this. So this is a very common expression for momentum operator in one-dimensional harmonic oscillator. So if you don't know this expression, you can directly remember this from here, that it's p cap is equal to 1 upon I under root m omega h cut upon 2 into a cap minus a cap dagger. Okay, a cap and a cap dagger are the creation and annihilation operators. So a cap dagger is the creation operator and this one is the annihilation operator. Okay, so in the next step what we have done, here we are given this expression. So we have simplified this expression. We have put the value of the expression, this expression of p cap here in the numerator and here in the denominator, and then we have simplified it. So when we put this expression of p cap in numerator and denominator, this expression is common, so this gets cancelled out. So I have not written this here because this gets cancelled out from numerator and denominator. So we are left only with the a cap and a cap minus a cap dagger operator only. So now we have to operate this here on n ket, and here in the denominator we have to operate this on this 1 ket. So when we operate this, as you may know that when a dagger operates on a ket vector n, it gives the eigenvalue as under root n plus 1, and this n ket changes to ket n plus 1. Okay, so we got this eigenvalue as under root n plus 1, and this ket vector n changed to n plus 1, and this bra vector n plus 1 was already there. So I have just taken this root n plus 1 outside, since this is the eigenvalue, and this minus sign is obviously here. So we have this expression, but when we operate a cap on n ket, we get under root n, and this the eigenvalue is under root n, but this n ket changes to n minus 1. So when the n minus 1 will combine with n plus 1, it will give 0. So because these are orthogonal states, so since n plus 1 will combine with n minus 1 and give 0, so I have not written that here. So you can solve that yourself to understand it completely. So similarly in the denominator, here we had the 1, here we had the n ket, but here we have the 1. the ket vector is 1. So similarly, when we operate on this, this changes to ket vector 2 and we get root 2, because here it was n and n became n plus 1. So here it was 1, so this vector will change to 2 and this eigenvalue will also change to under root 2, and again this minus is here, and again if we operate a cap on one ket vector, so a cap if we operate a cap on 1 we will get 0, and when this 0 will combine with this 2 it will give 0. Since similarly this is the orthogonal state, so I have not written that here, so only I have written when we operate a dagger on this. Okay, so I hope this is clear. Now this minus gets cancelled out, so and this n plus 1 becomes 1. This is 2 also becomes 1, since these are normalized states, and we get under root n plus 1 by 2. Okay, but we are given in the question that this expression is equal to root 2, but after solving we got this expression as under root n plus 1, so we just substitute that here and equate this equal to root 2. So we did that here, then we squared on both sides and got n plus 1 by 2 is equal to 2. Then after some simplification steps we finally got the answer n equal to 3. Okay, so which is given in the option 4, and the correct answer is 3. As you can see here in option 4 we are given answer 3. Okay, so option 4 is correct here, and the correct value of n is 3. Okay, I hope this question is also clear to all of you. That's all for today's video. Thank you very much and goodbye. Let's meet on another video. Okay.